Hello everyone, welcome to the Plexim presentation for the Next Generation EV and AV Virtual Conference. My name is Cici Zhao and I'm an application engineer at Plexim. In this session, I will present a model-based control design for multi-phase machines with a hybrid energy storage system for EV applications. Multi-phase machines are drawing more and more attention in EV industry right now. With the merit of duplicated set of windings, they usually show increased power density and also better reliability over their three-phase counterparts. Let's take the example of the six-phase PMSM we look at today. It's essentially a dual three-phase machine. So each three-phase windings can be supplied by an individual inverter, and each inverter can have its own energy source. For example, one can be supplied by battery packs and the other can be supplied by ultracapacitors. So this kind of hybrid energy storage system using both batteries and ultracaps is becoming a really popular solution in recent times. Let's take a look at the system structure. So here is the six-phase PMSM we talked about. Phase A, B, C makes one set of winding, and phase D, E, F makes the other set of winding with 30-degree displacement. And these are the two inverters supplying each set of windings, and inverter 1 is supplied by battery packs, and the inverter 2 is supplied by the ultracaps. So here the strategy is that inverter 2 supplied by the ultracaps, since they have much better dynamic response, then it will mainly react during speed signal change, for example, accelerating or decelerating for the dynamic torque. And then the inverter 1 supplied by the batteries, they will mainly supply the torque during cruising because the battery, they don't have as good as dynamic response as the ultracaps. But during steady state running, then the ultracaps will barely supply any currents. Since we are talking about the model-based controller design today, I would like to take a deeper look into the control algorithm. So here, just to mention that this whole control algorithm will be first implemented in Plex model and then later auto code generated and then flashed onto the microcontroller for testing. For example, here starting, we have an outer speed loop and then an inner current control loop. So we compare with the speed reference signal, our measured machine speed, passing through a PI regulator. Here we get the total machine current demand reference. And then through a low-pass filter, we distribute this total current with a low harmonic content to this inverter 1, which is supplied by the battery packs. And then the rest of the high harmonic content will go to the current demand of inverter 2, which will mainly supply the dynamic torques. And afterwards, each inverter's DQ currents are individually regulated by PI regulator. Then coming next, the cross-coupling effect of the windings inside the same machine are cancelled out here in the decoupling unit. And then afterwards, the voltage reference for each inverter leg is generated. And then afterwards, the gating signals are generated for each IGBT. So after we develop the control algorithm and then validate it on the offline simulation software, then usually the control engineers would move on to either hand program the microcontroller or use some sort of auto-generated code to flash the microcontroller. And afterwards, probably you go directly plug in this microcontroller to your motor drive power stage. But since this multi-phase machine is a relatively new field, probably you don't want to risk having any small mistakes here in the microcontroller which can risk damaging your power hardware. That's why here we would like to propose this hardware in the loop testing that comes very handy to bridge the gap between your offline simulation validation and then the real hardware validation. So the idea here is I will use this Texas Instruments 28069 microcontroller launchpad to run the real control algorithms. And then for the motor drive plant topology, it will be running virtually in this PLECS RT box in real time, so it can interact with our real control targets and test all different kinds of scenarios. And here the interface board is the one that will help connecting both targets together. Then just a few more words on the machine modeling part. In this demo, our machine can be modeled in two different configurations. One is the rotor reference frame. That's a classical approach. You model each winding as a controlled current source, but in this case, you will need some sort of snubber resistors, which can increase the stiffness of your system. And then the other approach is the constant parameter voltage behind reactance. In this approach, we model a controlled voltage source in series with a constant winding RL. So in this case, the advantage is that you can simulate open winding scenarios, and also because the winding inductance is a fixed value instead of a variable one normally, then it's more appropriate for real-time simulation. This is also the configuration we will use today. Move on, let's take a look at the PLECS model. So here is the top level schematics. We have one plant subsystem and one controller subsystem, and they are in closed loop connection. Opening the plant subsystem, you will see this six-phase PMSM we talked about. It's driven by two VSIs, and each VSI has its own source. In this case, we didn't model complicated battery model. We just used two fixed voltage source at 400 volts. But still, you will be able to observe the power demanded from the source and also the power recuperated back to the source. Let's take a look under the mask of the machine model. Here you will see this rotor reference frame implementation, and then also the constant parameter VBR implementation. Moving on to the controller subsystem, here the peripherals we use are from the PLECS TIC2000 target library, for example, the ADC, and then PWM generation, and also the quadrature encoder peripherals to derive the machine speed. And then in between is our control law implementation. For example, for the outer speed controller loop, we use our reference RPM to compare with the quadrature encoder measured speed passing through a PI regulator with anti-wind-up. And then here is the low-pass filter that is in charge of distributing the total current demand into the two inverters, one for fast dynamic response and the other for steady-state response. And afterwards, for each inverter's DQ current, it has its own PI regulator again, and then the decoupling, winding decoupling part is included here. So afterwards, the duty cycles are generated for each inverter leg. It's also worth mentioning that these peripheral blocks from C2000, they have the offline implementation, so the model can execute in an offline environment, but also once generate code, then these peripherals configuration task, which is usually quite cumbersome for the engineers, it will be directly generated by Plex coder according to your configurations set here. For example, PWM channels, switching frequency, and the deadband. And even the complicated microcontroller CPU interrupt routine can be graphically configured here. For example, the normal logic is the PWM, when the PWM counter reaches 0, it triggers a start of conversion signal for the ADC, and this is represented with this red dashed line. Coming here to trigger the ADC conversion, then the ADC module will convert according to the sequence you listed here, and then in the end of conversion of the last channel, it will trigger the system overall interrupt. And this sample time is your interrupt step size, and usually that is the inverse of your switching frequency. All right, let's take a look at the offline simulation result. So right now our speed reference is 300 RPM. I start the simulation. We can observe the inverter 1 and 2 three-phase currents. The rotor speed is ramping up, and here is the rotor positioning signal, and then also the torque. So we can see that after quickly starting up, the inverter 2 is mainly in charge of the dynamic torques, while the inverter 1 is slowly ramping up the currents. And once we're at steady state around 30 rad per second, that is roughly 300 RPM, I would like to do a speed reference jump to test the stability of the controllers I designed. For example, at this moment, then due to the step up of the reference, then inverter 2 again is in charge of the most of the dynamic torque, and then inverter 1 is ramping up its current until we reach 40 rad per second as the new steady state. Then the inverter 2 is barely supplying any currents from the ultra caps. Once this offline simulation in closed loop is validated, then I will move on and show you how to discretize each part of the model and generate code and deploy it onto our hardware targets. So just let me put back the speed reference to 300 RPM. Now let's take a deeper look at the hardware setup here. We have the RT box, and then here is our Piccolo launchpad. I will first plug in our launchpad onto the breakout board so that they can exchange, for example, PWM signals generated from the microcontroller can go into the RT box, and then the voltage and current measurement from the machine drive can go here to the ADC input of the microcontroller. All right, and now let's plug in the interface board. And here I will first connect the power cable for the RT box. And then turn on the power. And here the communication link between the RT box and my laptop is this Ethernet cable. So this cable will download the model of the generated code from the Plex side and then load it onto the RT box. And once the box is running, it will also retrieve the waveform data so that we can view in real time on the Plex scope on our laptop. So we'll plug in the Ethernet cable also. Then the similar communication link for the microcontroller launchpad is realized by this USB cable, which is also connected to my laptop. Now let's come back to the Plex model. I will show you how to generate code from the Plex model to run on the real hardware targets. In order to operate the code generation option, we need to engage this coder options window. And here we have two subsystems eligible for code generation. One is the plant, one is the controller. For the plant, I will run it on my RT Box 1, which is the one I have next to me. And the glass box is the name of my box. I'll click build here, and quickly you can see the generating code, making file, and then upload to the target. So now the box is already running. And then we do the same for the controller. Since I have from TI 28069 here on the launchpad, so this is the one I would choose. And similarly, I do build. And after the building and flashing process, then the microcontroller should be running, because I have some blinking LED logic so that you can observe here the LED is actually blinking. So now both targets are deployed and running online. Then I will enable the external mode and activate auto triggering for each platform. So right now you should see actually the waveforms are already running. It's just everything is 0 because we have some protection logic that at the startup we're not switching. So I have the logic here triggered by a dip switch on the launchpad. So if I flip up the dip switch, then quickly you will see the actual running waveforms on the Plex scope. So with this 300 RPM reference, we have at steady state already we are 30 rad per second. And then for inverter 2, we have barely any currents demanded from the ultra caps, and inverter 1 is mainly supplying the major torque. Then similarly, we can do the speed up test, and quickly you should see the dynamic currents reflected on the inverter 2, and afterwards steady state again. Now, after a hardware-in-the-loop validation of your real control targets loaded with your real control code, tested under different scenarios, then the engineers should feel more confident to move on and plug in their microcontroller to the real motor drive power stage. This is also the contribution we'd like to bring to this conference. I hope you have enjoyed our session. Feel free to join us for further discussion. Thanks for watching. Bye-bye.